Hello again. Today we are going to go over problems from chapter 24, I believe it is, the capacitance chapter. And so you'll have 6 recitation problems and then 4 homework problems. So let's look and see what we have. The first problem is problem number 5. A 7.7 microfarad capacitor is charged by a 125 volt battery and is then disconnected from the battery. When this chapter is connected to a second initially uncharged capacitor, C2, the final voltage on each capacitor is 15 volts. What is the value of C2? The hint they give is that the charge is conserved. So basically a certain amount of charge is put on C1 initially. And that amount of charge corresponds to the voltage. And so you're given the capacitance, you're given the voltage, you can figure out what that charge is. And so what happens is when you disconnect it from the battery and connect it to another uncharged capacitor, some of the charge from C1 is going to go to C2 until the voltage across each, or the potential difference across each, is the same. And so in this case, the final voltage on each capacitor is 15 volts. And so that will tell you what the value of C2 is. And so the total charge on each is equal to the initial charge. So some of the initial charge on C1 goes to C2 until they both have the same potential difference. Then we move on to problem 15. Dry air will break down if the electric field exceeds about 3.0 times 10 to the 6 volts per meter, meaning that you'll get a spark or some sort of discharge, or if you're talking about a cloud, you might get a lightning discharge. What amount of charge can be placed on a capacitor if the area on each plate is 6.8 square centimeters? So basically, what amount of charge can be placed in the capacitor so that the potential, or rather the electric field exceeds, or before the electric field between the two plates exceeds that amount? So if they're parallel plates, you know the relationship between, or you know how to figure out the capacitance, at least as a function of distance. And then the electric field is the voltage over the distance. And C, of course, is the charge over the voltage. So you have enough information from that to figure out how much charge it will take. That brings us to problem 28. A 0.50 microfarad and a 0.80 microfarad capacitor are connected in series to a 9-volt battery. So the capacitors are connected in series. Calculate the potential difference across each capacitor. So remember, they're carrying the same charge. And the total voltage, or the voltage across, the sum of the voltages across the two capacitors will add together to 9 volts. And they're carrying the same charge. It'd probably be easier in the first part to figure out the equivalent capacitance first, then figure out the total charge, which is going to be the same on each. And then once you know that, you can figure out part A. So it might be easier to figure out part B first, actually. And then for part C, repeats part A and B, assuming the two capacitors are in parallel. So in that case, you can figure out the potential difference across each capacitor very, very easily. And then once you do that, going to the charge is straightforward. Number 33. Suppose in problem 32 in figure 2425 that C1 equals C3 is equal to 8.0 microfarads, C2 is equal to C4 is equal to 16 microfarads, and Q3 is equal to 23 microcoulombs. Determine the charge on each of the other capacitors. Now, the fact that there's some symmetry in the problem is going to make this simple. That you'll probably be able to figure it out without necessarily going through all the math. And if the four capacitors all had different values for the capacitance, it might not be so simple. So keep that in mind. But you figure out the charge across each of the other capacitors, the voltage across each capacitor, and the voltage across the combination. So you have enough information. Look at the diagram carefully, or the figure carefully, and then set everything up. And work step by step. If you have any issues, don't hesitate to ask for some help. That brings us to number 46. How much energy must a 28-volt battery expend to charge a 0.45 microfarad and a 0.20 microfarad capacitor fully when they are placed in parallel and then in series? So they're connected in parallel. You have enough information that you can figure out the charge across each, and or the voltage across each, as the case may be, and that gives you enough information to figure out how much energy comes into play, and then how much charge flowed from the battery in each case. So again, the charge is the total charge in each case. And you can figure that out. You may figure that out before solving for the energy, depending on the configuration. But you can solve for both the charge and the energy, given the information that you have. And that brings us to number 62. Two identical capacitors are connected in parallel, and each acquires Q0 when connected to a source of voltage V0. The voltage is disconnected, and then a dielectric is inserted to fill the space between the plates of one of the capacitors. So this is kind of like problem 1. The charge is conserved, so the total charge is going to be 2Q0, and that's going to remain the same. So what happens is when you put the dielectric in, charge is going to flow from one capacitor to the other until the voltages across them are equal again. That the dielectric will change the voltage across each capacitor because it's changing the capacitance. So delta V is equal to Q over C, and C is changing, which means delta V is changing. And so charge is going to flow until the delta V's are equal again. And so that will tell you how to figure out the charge in each capacitor and the voltage across each capacitor. So you have enough information to do both of those. So that brings us to the homework problems, which again are due on Monday. So we have an electric field of 4.80 times 10 to the 5 volts per meter is desired between two parallel plates, each of area 21.0 square centimeters, and separated by 2.50 centimeters of air. What charge must be on each plate? So you're given the electric field, and remember, we know what the electric field is between two parallel plates. It's sigma divided by epsilon naught. And so we're not given sigma directly, but we're given the area and asked to figure out the charge. So we have enough information to solve that problem. Then we move on to number 37. Determine the equivalent capacitance of the circuit shown in figure 2427. So you can look at that figure. If you have any questions, you can email me for help. If C1 is equal to C2 is equal to 2C3 is equal to 24.0 microfarads, how much charge is stored on each capacitor when the voltage is equal to 35.0 volts? So figure out the equivalent capacitance first, which is part A, and then sort of work your way back. When you know the equivalent capacitance and you know the voltage, then you know the total charge. So that should tell you the charge on some of the other capacitors. And you work from there. Remember, if capacitors are connected in series, you have the same charge across each. And you can have equivalent capacitances connected in series. meaning you have combinations of capacitors that are connected in series with each other. So keep that in mind. And so you can figure out the charge, and if you have a segment where the capacitors are connected in parallel, the voltages across each capacitor in that segment are going to be the same. But if you have any questions figuring that out, don't hesitate to email me and ask for help. And then the last problem, or rather, 45, in figure 2427, and again, these figures are in the book. Let V equal 10.0 volts and C1 equals C2 equals C3 equals 22.6 microfarads. How much energy is stored in the capacitor network? You can figure out the equivalent capacitance of C1, C2, and C3, or the total capacitance. And if you know that, then you have enough information to figure out the energy that's stored in the capacitor network. And that brings us to the last problem. A 3,500 picofarad air gap capacitor is connected to a 32-volt battery. If a piece of mica fills the space between the plates, how much charge will flow from the battery? So initially, it's fully charged. And then what happens is you put a piece of mica between the conducting plates in the capacitor. And that is going to increase the capacitance, which increases the amount of charge it can hold for a given voltage. So you want to figure out how much charge is added when you put the piece of mica in. So those are the 10 problems you're going to be working on for chapter 24. Again, if you have any questions, whether it's a recitation problem or a homework problem, let me know. I'd like to see videos of the recitation problems up by tomorrow, if possible. And if you have any issues with that, let me know. Otherwise, good luck, and I will talk to you soon.